There is a few rules to participate in the event. So this webinar is being transmitted on Video Saúde Fiocruz YouTube channel. This webinar is being recorded and will be shared on the Global Health Network LAC platform. Please use the YouTube chat feature for any technical issues. Please post your questions on the YouTube chat feature. And we have dedicated time allocated for questions and answers, so we'll try to get through as many as possible. And the agenda of the seminar is a welcome introductions, presentation of the ensemble model, interactive sessions with a discussion, presentation of the teams participating in the challenge, and interactive session with a discussion and questions and answering questions. So now we move for the presentation for Flavio Codeso. The first one presentation. Welcome, Flavio. Thank you.
Thank you. I'm going to share my screen here. Okay, can you see my presentation?
Yes.
Thank you. Well, welcome again. Good morning for those who are in the morning. Good afternoon for those in the afternoon. As you already heard, this is the second webinar of the InfoDengue Mosqlimate Challenge 2025. And this event is where we present the results of the ensemble of all the modules that were contributed to our challenge. This event is also known as the sprint. And I'd like to say that as we sprint towards having better and better models to forecast dengue incidence, the Aedes mosquito is also sprinting to enlarge its territory, helped by our current ecological and climatic crisis, and by the deterioration of life conditions for humans on Earth, which help the mosquito to explore new territories and transmit a whole lot of viruses that they are capable of. Our enemy here is not the mosquito. Our enemy are the diseases and the tool that we have to solve this are not the models, but the improvement of life conditions for every human on Earth. I just wanted to say that before we started. So let's get started. So this is a brief outline of my presentation now. I'm going to go really quick over the technical details. The goal of this presentation is to be a slightly technical presentation in which we'll present the result of the combination of all the models that were submitted to our second edition of our challenge and of the sprint. And this entire initiative was organized by the Mosqlimate Research Group, and you can go to our website on mosqlimate.org, and is supported also by the InfoDengue project with data. And here's the website for the InfoDengue. You can also visit. And the whole initiative is funded by the Wellcome Trust. So this model is not made just by us. Of course, it would never happen without the help of our participant teams. And this year we were very happy to have 15 teams from around the globe which submitted 19 predictive models for dengue in Brazil. This is no small feat. They put in a lot of work because training and fitting this model to a huge amount of dengue data that we made available for them, it's a lot of work. So we're really thankful for all the work that they put into this. So this is a brief list. There are not a lot of details, I know, but you can always check the full details about the teams in our full report to which I'll give the link for you to download and read after my presentation. So the models, like I said, were initially 19 models, but for some issues, not all models were able to be included in the ensemble. So those are the ones that got in to form the final ensemble model, which is a combination of all the models. And we tried here on this table to make a very, very loosely defined characterization of the type of methodology underlying each of the models. This is not at all accurate. It's just for you to have an idea of the variety of methodological background that is involved in trying to predict dengue. So moving on, let's talk about how this whole exercise of creating an ensemble from this model was done. And before we can get to that, I should say a little bit more about our inclusion criteria. I said that we started with 19 and we had to exclude four models. Three of them were not eligible because of slightly uh, inconformities with the sprint rules, and one did not submit the forecast for the full set of validation sets in 2026 forecast, so they were not included. So repeating now, only 15 were included in the final ensemble. But when we get, giving a little bit of a spoiler here, we're still not in the results that we're going to present today. But to give a little spoiler about the challenge that is to be, to build such an ensemble, we jokingly call this problem a puzzle because if you look at this heat map here, don't worry, I'm going to explain all these colors and numbers to you. It just describes how complicated it is to pick a best model. There's no best model, single best model. It's very hard. So on the columns of this big matrix here, on the columns, you see in words here the model that was best for this state, the state of Paraná here. But since they were evaluated at different years, 2023, 2024, and 2025, it was the one that has the best average ranking for the state of Paraná, but it was not the best in every one for every year. So it was the best, the first in the ranking for 2025, but it's only the seventh in the 2024 and only the third in 2023. So that's why it's very hard to say, okay, this is the best. Or sometimes the model can be, for instance, this one for Rio. It was the best in Rio, the second best in Rio for 2024, but then 2023 didn't fare as well. So when we look at for all the states, it's very rare that we find a model that is 111 or 222 at least. This one is pretty good. Like for Minas Gerais, it was first in 2025, second in 2024, and then second in 2023. So it's pretty good. But for most of the models in the states, there are a whole lot of variation. So when we go to try to make a combination of this, we have to take all this into account. I'm not going to go into all the details of how this was done, and all the gory details will be on our final report, which will be available to you. But for this presentation, there's no time for me to go into all the details. But I'm going to try to give a sufficiently detailed overview so that you can understand. And you can always ask questions at the end. So moving on, what exactly do we combine? So all models that participated and were selected for the ensemble, they submitted predictions consisting of the following percentiles. So they had the median, the percentile 50, the median number of cases predicted for a given week in a given state in a given year, but they also gave the other percentiles, the 25th, the 10th, the 5th, and the 2.5. And also for the other side, for the upper side of the interval. So we had many uncertainty intervals around the median that were submitted by each of the models. So in order to combine these models into a single ensemble, we simply took the median of all these percentiles for all the predicted intervals submitted by the models. This approach was not originally our idea. It was originally proposed in this paper by the COVID Hub, and we kind of liked it. It's not the same methodology we used for last year's sprint, but the results were very similar to the methodology we adopted last year. And since this methodology does not assume a parametric approximation for the predicted distributions for this year, we decided to go with a simpler approach. Okay, so one other thing that I need to say is that the models were scored using a statistic called a weighted interval score, which we'll refer here to as WIS. And since WIS is it has values that vary with the scale of the prediction, so states with larger number of cases will have larger WIS values, WIS scores, than states with a smaller populations, therefore smaller number of cases. They're not in this raw form. They're not compared across states. So we normalize the WIS scores for every model on every state by dividing by the total number of cases in every year, so that now we then rank the models using the normalized list. So that's all that I wanted to go through in terms of the math about how we did this course. Oh, there's a little bit more. But then it's not enough for us to rank. We also want, and then why do we rank them for? We rank them because we want to select a subset to build an ensemble from. So, and then we needed a little bit more of math to figure out how better is our ensemble, or worse, it could be, than the individual model. So for this, we use this thing that's called a skill score. We say that the models have a skill to forecast, an ability to forecast well in the next year. And the ratio, so this form of ratio between the skill of the ensemble and the skill of each model will give us a comparative measurement. And all you need to remember from this is that positive values for the SS will indicate that the ensemble model will outperform the individual models, okay? Because this will help us understand some of the charts that I'm going to show next. So now we have a chart of the SS for every model for all the 3 validation years, 2023, 2024, 2025. And we see here in orange, in the top above the 0 line, all the predictions where the ensemble was better than the individual model. And each dot here is a prediction for one model. So when this dot is orange, means that the prediction from the ensemble is better than it. And the blue ones means that the model was better. So there's a lot of situations where, if we take all the models, there's a lot of situations where the individual models are better than the ensemble. So why should we use the ensemble? So that's a very important question that we need to answer by saying that the ensemble achieves a more consistent prediction across all states and across all years. So while a certain individual model, while being very good at a certain year state, it can be very bad in others. So by doing the ensemble, we guarantee that the average performance when predicting for across the board is going to be better, right? So that's why we do the ensemble. That's why we will use the ensemble to predict for next year. So after looking at those charts that I just showed you, we decided, okay, we don't need to make an ensemble. Actually, there was a very sophisticated optimization process to reach this result that you're seeing here. But we don't need to take all the models to build the ensemble. We can take only the top 5 models for each state to build the ensemble for that particular state, and across all years, of course. So therefore, in this case, we actually doing the WIS normalized for 2023 and 2024, and showing how better on average the ensemble was across all states. So the ensemble was on average 12% more accurate than the best model, which is good. That's something we can back it up. So moving on, so that's the methodology we're going to stick to. So finally, reaching the main thing that you're waiting for in this webinar, the results. So we'll start by the South region, and we'll start by showing you predictions of weekly incidence for 2026. So let me teach you how to interpret this charts. So here we have the South region. So we have here the first chart for Paraná, the second for Santa Catarina, and the third one for Rio Grande do Sul. In blue is the prediction of the ensemble model. In red, the red line, I hope you can see it, is the prediction of the best model for that particular state. And in the dotted line is the actual weekly incidence of probable cases of dengue for that state in the previous year. Actually, in this year, 2025, because we are predicting for 2026, okay? So we can see that the predictions are pretty close to what we had this year. Our prediction for next year are pretty close. And I forgot to mention that this shade of blue here, or purple, or whatever, is the predictive interval for the ensemble. So the ensemble has a median prediction, which is represented by the dashed blue line, but this area here is how much it can vary. It can vary between this. This is a 90% certainty. So the same thing applies for Santa Catarina and Rio Grande do Sul, the same rules for interpretation, and that's going to remain the same for the other states that I'm going to show. And you can see that for Santa Catarina, we are predicting slightly higher incidence next year, but for Rio Grande do Sul, we'll predict a slight less, about half the incidence we had this year. Okay. So moving on, we decided still in the south, we decided to also show our predictions in cumulative incidence, so that we can have an idea of the total cases we can expect for next year. So what are the total cases? The total cases is the end of this line here. See, this is how the cases we predict they will accumulate throughout the year to reach this incidence. Note that even though again, the results are more or less the same for the cumulative. For Paraná, we are predicting less total incidence. For Santa Catarina, we predict more, and for Rio Grande do Sul, less than this year. And it's very simple. I hope it's simple to understand. And I should say that even though it's in some cases we're predicting a better situation, it's still a pretty high incidence, if you ask me. So we should be careful, and then we have an opportunity to try and control and reduce those predictions to a more acceptable level. If you move on then to the southeast, and now we have São Paulo here, Minas Gerais here, Espírito Santo here, and Rio de Janeiro. We see that we predict a lot less for São Paulo next year than we had this year. As you can see here the difference of these lines. For Minas Gerais, a slightly higher, the same for Espírito Santo and Rio. Don't worry, because at the end I'm going to show them all together so that we can understand better how they compare across all states. But I have to give you this detailed view first, and then we look at the more side by side. So cumulative incidence for Southeast, here we go, same qualitative results, less for Sao Paulo, but we are expecting almost 1,000 cases per 100,000 individuals. So I should say that this incidence numbers are per 100,000 individuals in the population, in the overall population. So this is not a raw case of numbers, a count of numbers, is incidence, which means for every 100,000 people in the population, we have this many cases. We expect this many cases. So we for Minas Gerais and Rio, we expect pretty much the same in better situations for São Paulo and Espírito Santo. Moving on to the Midwest, we have Mato Grosso do Sul here, Mato Grosso, Distrito Federal, and Goiás. And in this case, the predictions are telling us that we'll have a year very similar to 2025, the year that we're on. And especially for Mato Grosso, we can even say that we can be pretty certain of that, because our uncertainty interval here is much more and much narrower than for the others. So there's, pretty sure that's going to be a typical according to 2025 standards year for dengue. Okay. Cumulatively speaking, it's interesting that we can see that the cumulative charts show us more clearly, because of the scale of the graph, that the cumulative incidence for Mato Grosso is actually going to be slightly lower than this. But for most of the states, we have a similar number. Moving on. Northeast, we have this 9 states here, and we expect our expectations for next year also are pretty close in this chart here, in all these charts, let's say. If we look at the cumulative, and then we have a better perspective, we expect more cases, more cumulative incidence for Alagoas, and a little less for Piauí, but and a little more for Ceará. And the other states are pretty similar. Moving on to the North region, here we have Acre, Pará, Tocantins, Amazonas, Rondônia, Amapá, and Roraima. Since these charts are drawn to the same scale of incidence so that they can be comparable, some of the the states with less incidence, they get squash on the bottom. So there's no, we can either make them comparable or make them easier to see. So we have to live with that and this type of visualization. But it's funny to see that Acre has a pretty high incidence this year, but it's expected to get better next year. So let's hope that managed to be true. In terms of cumulative incidence, we expect a substantial improvement for Acre, a small improvement for Amapá, and slightly worse conditions for Tocantins. In order to give a better sense of the overall pictures comparing all states, we make the chart, which means through which we can compare again the cumulative incidence. It's like the last point on the charts that I just presented for cumulative incidence, but placed as a single point on this map with the X, the black X marking the cumulative incidence we had in 2025. And we can see here that our predictions sometimes fall above, like for Minas Gerais, sometimes way below, like for São Paulo. But for all cases, if you look at our uncertainty, our bars here, this interval, this uncertainty interval for the prediction, they all include the X, and we can interpret this as for all states, next year is not going to be substantially different or significantly, if you like this term better, different from this year. However, this graph is still interesting because it will point us the directions in which we expect these changes to occur. So we do expect, for instance, a lot less cases in São Paulo, and perhaps quite a bit more, and a lot less for Acre. But yeah, and so that's what this chart tells us. Okay. But the best visualization for comparing the whole thing, I think, is this one. Let me explain to you how to read this map. So on this map, when you have a color that's close to white, it means that our predicted total incidence, cumulative incidence for 2026 is indistinguishable for the total cumulative distribution for this year, for 2025. The warmer colors is when our predictions for next year are higher than what we had this year. And the cool colors, the blues, means that we are predicting less dengue for those states next year. So that's how we read this. But it's not the whole story, because we have here numerically, in an easier to read fashion, our predicted incidence for next year. And for instance, even though we in the Midwest, for instance, we had most good predictions, we still have Goiás with an extremely high incidence, not much higher than what we had this year, but still high. So we need to pay attention to Goiás. And some things can be tricky and should be read carefully. For instance, Tocantins has a very some extreme for the red scale, so meaning that they are more than twice as much incidence for next year. We're predicting twice as much incidence for next year than this year. And this, so there's a percentage change, okay? So if it's 100%, it's the same. So it's 200% is twice. If it's 50%, it's half. So, but Tocantins has a much lower incidence than, for instance, Goiás. But Goiás is not that much worse than last year. So you have to read both things. But have to read both the colors and the values. Not reading just one of them is not enough to understand the situation and where it's going. You can see here we grouped here also by regions. So we have here the first block here is the states in the south. They're mostly a better situation for next year, with the exception of Santa Catarina. For the southeast, the second block here, we have a very high incidence for Minas Gerais predicted, worse than this year, but for all other states, we're getting better. So the situation is good for southeast. Doesn't mean that next year is going to be really easy, but it's going to be better, which is good. The third block, or the third block is the Mideast, the Mideast, Midwest, pardon me. So we have the champion of incidents for next year, which is Goiás, but it's just following what's going on now. So I would assume that with at least on the bright side, people who are in charge of trying to improve the situation is already well aware of the situation of dengue in Goiás and will be able to do a good job for next year to try to prevent us from reaching this destination. And but overall, if we think about overall for Midwest, we have a pretty high average of incidents, more than Northeast, more than the North, more even higher than the South on average, but on a par with the Southeast. And finally, well, not finally, we have the Northeast, which even though most states are getting worse, they are not too high. So that's on the bright side, but they're mostly on the warmer colors, meaning that situation might be higher for next year. We should also stress very much that these predictions are not what's going to happen. The reason why we make this prediction is that so that we can do something to to try to avoid this to happen. But that's our best guesses. So finally, for the North, situation seems to be getting better in most states, with the exception for Tocantins, and with lower incidence with the exception for Acre, which is coming from a very high incidence this year. So this is how you read this chart. So it tells you good things and bad things, and you should be aware of how to interpret this. It's not easy, but it can be very useful for those in decision making. I would like to say also that in terms we've been comparing throughout our results our incidence values to 2025, which is we decided it would be a good idea because 2025 is the year that we're on, so we have a good memory of how it was this year. So it's easier than I try to compare it to, like, say, 2012 or some other year that you don't remember exactly how it went. But I should say also that 2025, we had a lot of cases. It was not, in terms of the whole history of dengue, it was a high year. Sorry, it was a high year. And so even if we're saying that we're likely to stay at the same level of 2025, it's not exactly how we would like it to be. We would like to be less. But 2025 also was a lot better than 2024, where we had the highest year ever in the history of dengue in Brazil. In 2025, we had more than 2024, we had more than 6 million cases of dengue. And in 2025, we had a quarter of that. Okay. So we are on the way down, hopefully. And that can be also another good news. Good news is the fact that next year it's shaping to be a La Nina year. And we've found out, and not only us, but also many colleagues that study climate and dengue, that La Nina years tend to be associated with less incidents in Brazil. So hopefully La Nina is going to help us, and we will not have this level of incidence next year, but something less. But that's for now is our best guess. So I would like with us to end this presentation by acknowledging the whole Mosqlimate team. This whole work took a lot of people to put together. So I'm showing just the pictures because it's a lot of people. And we're ready to do this again next year. So if you would like to participate, if you would join in any other way to help this event, please reach out and talk to us. So with that said, I'd like you to save the following dates. On the October 31st, in 2 weeks, we're going to have another presentation, this time less technical and more focused on what we can do about it, bringing together people from the Ministry of Health and decision makers in the public health arena, and and also keep watching our website, which is indicated by this QR code, because in the beginning of 2026 we'll be announcing the important dates for the next sprint. Okay, so with that, I thank you, and I very much for being here, and for, if you can, spread the word of what we're doing. We will be very grateful to all of you. And this is another website with the report, the full report, like I promised you, the full report of what I've just briefly described in this presentation. Thank you.
Well, thank you, Flavio, for this great presentation. Now we open for questions and discussion. Anyone here in this room had one question for the participants sprint? If you don't, so in the chat in YouTube we have two questions. The Eduardo Conceição. First, we said, thank you for this lesson, Dr. Flavio. In addition to describe the two descriptive models, have you ever used any multivariate tested based on PCA, principal component analysis, combined with cluster analysis as epidemiological predictor?
Thank you for your question, Eduardo. Yes, we will have a few brief presentations of some of the participants that agreed to make a very short presentation today. But all I can say to you is that you can check our report, because we have links for all the implementation of the models. All this model had to deal with a lot of data. So clustering analysis and dimensionality reduction through PCA were some of the techniques that were present in many models, because those models really combine a lot of methods in order to reach their final prediction. So I invite you to look there.
So Eduardo also And had a question. The overall projections is for a reduction in cases by 2026. How reliable is the regression model?
Well, yes, for the first part, yes, we predict less overall. And how reliable? Well, uh, you saw the uncertainty bands. That's all I can say. Yeah, it's not a prophecy. It's a prediction with uncertainty.
So Joaquim Neto asks, instead of using the incidence in each state, could the prediction model be based on regions of Brazil bioma?
Well, that's a great point. We had decided for the sprint because when we organize a sprint of this magnitude, we need to set up a general design for what is going to be predicted, so we have comparable design, comparable results. So even though some models do use biome information to inform their predictions in the state, the predictions were grouped by state. So we are predicting the state incidence. Where there was a choice, there was a decision that was made when we define how the rules for the competition uh, were going to be. Thank you.
Another one for Rodrigo Gurgel. How to deal with wide confidence interval, blue shadows, as I understood, presented by ensemble models.
Yeah, that's a question that is all over statistics, right? Uncertainty is something that makes people uncomfortable when they're making predictions and they cannot say that's going to happen. That's exactly that. Nobody can do that. Statistical models are about understanding the variation in estimates. So we stand by our uncertainty, and in a way, I prefer to have a somewhat broad uncertainty interval, but to have an unbiased estimate of what's going to happen than to have a very narrow interval and then my median be above or too much above, too much biased, above or below what ends up happening. So we shoot on this model, we shoot for having an unbiased estimate as much as we can, given all the limitations of information that we all live in. But yes, we hope that our estimates are unbiased, but our uncertainties are what they are.
So thank you for the answers. And if anyone had more questions, we can move to the team leaders presentation. Well, each team has 3 minutes to share a short overview of the model and main results. So we start with Eduardo, and I have to share my screen. Is correct, Eduardo?
Yes, I can see your presentation. Hello, everyone. My name is Eduardo. I'm part of the Mosqlimate project. Can you everyone hear me?
Yep.
Thank you. And I'm here today to briefly explain the two models that I submitted to the second edition of the sprint. So my models have the ID 155 and 156. You can check them and the code in the Mosqlimate platform. And my models are really simple. Both use the same architecture. What change between them is the covariates used during training. So my models are based in long-term short memory neural networks. And in this figure, we have the architecture that was used to build the model. So I have basically two extra LSTM layers. And in the output, instead of predict a single time series, as is common in this kind of model, I use the PyTorch probability to predict the parameters of a log normal distribution. And to train the model, I use the S-loss function, the weighted interval score. Fabiana, can you go please to the next slide? So in this slide, I talk a bit more about the covariates used by each model. The models were trained at the regional health level scale. And in the base model, I use just the case count and the epidemiological week and the normalized population of the regional health. And in the second model with covariates, I used also the El Nino Surface Oscillation Index and the biome predominant in the regional health. Can you go to the next slide, please? In this slide, I have the workflow used to train and forecast the model. So I trained a specific model for each macro region. And as I said before, I use the data at the regional health scale. And to train the model, I use the data after the epidemiological week 41 of 2015 up to the epidemiological week 25 of the last year that is being predicted to be according to the sprint rules. And I use the early stopping to avoid overfitting during training. And after I train the model for each macro region to generate the states for the forecast for states, I applied the model for each regional health of the state multiple times to generate multiple samples. And I sum these samples and get the prediction intervals at state level. That's it. That's a really brief explanation. How I said, you can check the code and more details in the Mosqlimate API. And I am here to answer any questions later. Thank you.
Thank you, Eduardo. Now I invite to Julie to present the model.
Okay. Hello. I cannot start my video. I don't know if there's something blocking it. You cannot start your video because the host has stopped it. I don't know if may I continue without it?
Yeah, please.
Okay. Okay. Good morning, everyone. Okay, now I can start it. Our model is LLM model for time series. We developed this model together. Me, Julie, Davi, and Beatriz. We're all postdoc students at FGV. Can you go please to the next slide? So we organize the data by municipalities. Actually, the data was already in this way, and we decided to use a large language model that is trained on top of time series. It's similarly of what GPT models do, but they do train other models on top of like a large corpora of textual data or images. This model is specialized in time series. So they put like thousands, billions of time series on this LLM, and then now given like some time series shape, it uses like its experience, like other time series it has seen in the past, then try to make a prediction. So this model was developed by AWS, like the Amazon company, and it's a very nice and very like modern framework. So we wanted to bring like this kind of new kind of approach for forecasting, and we used this model by the tool AutoGloom. It's like some kind of library that makes it easy to be used. So if you go to our GitHub, that's on Mosqlimate page, you see like how easy it's to implement this model. And the model itself gives us like intervals, everything that the sprint rules have. So it was very like straightforward to apply it. And then we had to do some post-processing, like sorting quantiles to have this monotonicity. We believe there's like some problem in the implementation of this model, in which the quantiles, they were not like very right, so we had to fix it by hand, but we did it, and then we think the results were great. And if you can go to the next step, to the next page, sorry. Those are the two papers that we use for like this modeling. And this is like Chronos, the paper from Amazon, and AutoGloom, that is the library we use to connect to the model called Chronos. So this is like our model. It's LLM, and if you guys have any questions, I'll be happy to answer.
Thank you, Julie. And now, Flo.
Hi there, my name is Chloe Fletcher. I'm from the Global Health Resilience Group at the Barcelona Supercomputing Centre. Just to give a very fast overview of the GHR model, for this year's sprint, we used an interaction modelling framework to generate weekly dengue predictions using monthly climatic, oceanic, and classification indices. We specified a Bayesian hierarchical mix model using weekly dengue case counts at the health region level as our response variable, which we assumed to follow a negative binomial distribution. We log transform the distribution mean, combining the dengue incidence rate with the annual population per health region, and then use the R-inler package to find statistical relationships between the historical dengue incidence and our fixed and random effects. For the fixed effects, we included a three-way interaction between the lagged climate covariates. So that included a temperature anomaly marked by T, a long lag drought index marked by L, and a short lag drought index marked by S. And that represents the seven of those fixed effects termed in pink, as well as including an additive term for the absolute temperature marked by A. And for these 8 terms in parentheses, we determined different effect sizes by Köppen classification using random slopes. Within the model, we also included a term for an oceanic index marked by N and a binary state level index marked by C. For our random effects, we included weekly, yearly, and spatial effects for our model fitting to account for unknown and unmeasured variation in the dengue incidence. Next slide, please. Importantly, for forecasting and the validation test, we removed the yearly random effect as this led to an improvement in the model's predictive performance. Next slide, please. So to represent the model in a more accessible way, our final prediction model included a three-way interaction between the 6-month mean temperature anomaly lagged by 1 month, the 12-month standardized precipitation evapotranspiration index, or SPI12, lagged by 3 months, and the SPEI3 lagged by 1 month. We also added the 6-month mean absolute temperature lagged by 1 month, and all 8 of these terms, again in parentheses, were specified by Köppen classification. We also added a nonlinear term for the oceanic Niño index lagged by 7 months, and this binary state-specific term whether cases were pre-2018 or not to account for change in transmission pattern. We also included a state-specific weekly random effect and a structured and unstructured health region level spatial random effect. To calculate levels at To calculate predictions at the state level, we aggregated up from the health region level, which we produce these forecasts using observed variables, seasonal forecasts from the ECMWF that we bias corrected, and at longer lead times outside the seasonal forecasting window, we use climatologies. Just to give a very quick overview of how well the model performed during the 3 validation tests. Sorry, next slide, please. On the left, at the national level, the model underestimated cases in the first 2 seasons, which is unsurprising given these were record-breaking years, but managed to capture that sharp signal in the 2nd season, with the final season actually being well captured at the national level. On the right, by state, we can see the model did better in the northeast and midwest of the country and less well in areas with historically lower incidence. Last slide, please. And for the dengue season that was just commenced, our model specifically has predicted under 1.5 million cases at the national level, meaning that we expect to see a smaller outbreak year compared to the last 3 seasons, with a peak occurring around April 2026. And on the right, we have our state level predictions, which will partly contribute to the ensemble model. So many thanks for your attention. Please do feel free to get in touch with our team if you have any further questions. Thank you.
Thank you, Chloe. Hadrian?
Hello, my name's Hadrian, and I'll be talking about our model, which is the Imperial TFT model. So we wanted to forecast the weekly number of dengue cases per state in Brazil. And to do this, we used both time varying and static covariates. So we used the population weighted aggregation of the municipality level climate data, namely temperature, precipitation, relative humidity, and pressure. So we got the municipality level values and then weighted them by the proportion of the state population living in each municipality. And we applied this same population weighting scheme for the static covariates, where we used the proportion of the state population living in each Köppen climate class and Brazilian biome. And we used this as input. Oh, sorry, next slide, please. We use this as input to our primary model, which is the temporal fusion transformer, or TFT. And this is a deep learning-based method developed by Lim et al. At the University of Oxford in collaboration with Google. And we chose this model for 4 main features. First, at the start of the network, it features these variable selection networks, which then allow it to automatically choose the most important inputs, and also lends the model some interpretability because the variable weights that it outputs can be seen as how important each input is to the output forecast. Second, it has scalable complexity. By using these skip connections, it can skip over parts of the neural network if they're deemed to be unnecessary during model fitting. Third, it's flexible with the use of covariates, so it can accept static, past, or future covariates. And for this forecasting challenge, we leveraged on static and future covariates. And lastly, it features a multi-head attention block for learning long-range temporal patterns. Next slide, please. So to tune this model, we split the first training set into multiple train validation folds, and then we tuned the TFT hyperparameters using the Optuna Python package, optimizing on mean quantile loss across 3 validation sets. So we did this in order to tune the model while respecting the data constraints that are part of the challenge, essentially the gap between the target and the training sets. And then to train the model itself, first we tuned and fitted a random forest model to generate forecasts of our climate variables. And these climate forecasts are fed into the dengue models, which then generate the dengue forecasts. So we trained the TFT using an incremental fine-tuning approach. So this means that we took the TFT that would forecast for target 1, and then we got the new data from the second training set minus the first training set, plus some replay fraction to prevent the network from forgetting. And then we retrained the already trained TFT in order to forecast for target 2. And we repeated this process until we had forecasts for each of the targets necessary for the forecasting challenge. So all the data we used here were provided by the challenge organizers, and we didn't use other external sources. So thank you.
Thank you, Adrian. Davide?
Hi, everybody. Can you hear me?
Yes.
Yeah, thank you. So I'm Davide Nicola from Easy Foundation, Turin in Italy. I'm going to show you the model we create for the sprint challenge. Can you please change the slide? Thank you. So the model we create is a mechanicistic compartmental model in which we study both the evolution of the dengue disease in human and in the vector. But as you can see, the vector is divided into parts. The green one represents the adult compartment, while the orange compartment are the aquatic phase of the evolution, the biological evolution of mosquitoes. And we just are also interested in weather-dependent parameters. For example, pi and theta are the handling rate and development rate that are weather-dependent, and mainly they depend on average temperature and average precipitation of the day. So can you change the slide, please? To calibrate this model, we use a Markov chain Monte Carlo model method using a negative binomial likelihood to fit the parameter. And the parameter we fitted were the one that are part of the force of infection, mainly the human to vector transmission probabilities and the vector to human, but also we decide to fit the percentage of susceptible population because we see that each year the number of population that could be infected will vary based on the attack rate of the year before. And so there is a mistake with the slide. Okay, sorry. No, I need those. Okay.
It's okay? Sorry.
Nothing. So to make this, we made over 10,000 simulation, and we take the median from all the simulation to find the best value to fit the observed incidence. And we use these parameters as a proxy to inform the forecast process. Can you change the slide, please? Thank you so much. As you can see, this is an example of one of the states. This is Sao Paulo state, and this is the fitting process before the forecast. We decided to use a 3-year period for fitting the parameter to find the best parameter to inform the forecast, because we want to avoid the extreme case like was 2024. So to use an average between normal dengue diffusion and extraordinary like the other one. This is our work. We are ready for being touched to discuss any other question you want in the future. Thank you so much.
Thank you, David. Sorry for technical issues. So I invite Márcio to present.
Hello, my name is Marcio, and my model's name is Stranger Attractors, but there's no attractors in the model, just the name. And The model, yeah, we can pass the slide directly to the equations. Next, please. And next, again. Okay. This model comprises of two main drivers. The first one is the drivers that environmental pressures on the infections in state, and the second one is comprised by the transit of people between states. And you can pass this slide, please. So the first component, since is a periodic environmental phenomena, I choose to use a Fourier series expansion, but not a vanilla one. I choose a Gaussian rapid Fourier, both because it has a exponential decaying coefficients for the expansion, and also have it's more suitable to fit the shape of pools instead of using step functions. So for the seasonality, I have this Fourier series expansion with rapid Gaussian, and for the transit between states, I have a gravity model. It's a variation of the classic Newtonian gravity, since instead of use a symmetric mass for the each of the masses, I have an overall population for the sync one, and for the other states that are linked to this one, I have prevalence population. So this gravity model is asymmetric. So with these two components, I created a linear function, and I linked it to a beta distribution through a sigmoid function, and comprise it. You can pass for the next slide, please. So using this link function, I plug it in a beta distribution and inferred the infected population using a beta binomial conjugate, and to address those states with minor incidence records, I choose to use a partial pooling for the hyperparameters of the distributions that I use it in this model. And that's it. It's a simple model. Thank you.
Thank you, Marcio. And so thank you so much, Marcio and everyone. Those in really interesting, insightful presentations. Great to see how each team approached this challenge. And well, now we open for questions. Oh, thank you, Amanda, for sharing the YouTube questions here. Lincoln Swissdeck asked to Eduardo, which microregions have you used and how are they geographically delimited?
Hi, Lincoln. Thank you for the question. The macroregions was defined by the political macroregions of the country. So, for example, the South macroregion contains the states of Paraná, Santa Catarina, and Rio Grande do Sul. And there is another question asking about the data interval that I used. And the sprint organizers shared with us a data set with data up after 2010. But I decided to use the data after 2015 because that was the period when the majority of the regional health has a significant number of cases notified.
Okay, thank you. Any questions? So, well, thank you again for the participating and contributing to all the institutions that contributed with the challenge. To close our session, I now like to invite Flavio, Dr. Flavio Codeso, our coordinator, to share a final remarks and about the seminar and about the challenge before we officially close the session.
Thank you, Fabiana. Can you share the ending slides? Do you have them?
Okay. I know.
Well, I would like just to thank everyone again. I think that I would like to share also that how much of a challenge this whole thing is. I think you had a glimpse of the complexity of the models that the teams used, and that's exactly the goal of our sprint. We would like to get the best ideas from whoever wants to participate. So if you are out there and if you have a different idea, please join the next year's sprint and try and get your ideas to do a better job for this data set. So I'd like to with that remind you that all this material that was presented here is going to be available to you. Maybe Fabiana, next slide with the links.
We have one.
Yes. Okay. But there's yeah. In any case, the video is going to be live on YouTube as it is, but it's going to remain available. And you have already caught the QR code for our full report. And there is also going to be a site for you to rate our event. I think we have the QR code for that, Fabi.
What?
The QR code for the evaluation of the event.
No, I put in the YouTube message right now.
Okay, fantastic. So yeah, so that's all we have for today. I thank you again for being here, and please respond to our survey by giving your opinion about our event here, and please join us on the end of the month for the next webinar. Thanks a lot, and have a nice day, all of you.
Fabiana, did you receive my slides?
No.
No?
Hi, everyone. Just please be quiet for a second. Thank you. We're finishing transmission on YouTube.